Chapter 1, Stress, Normal, Shear, and Bearing Stresses in Design. Example number 2. So let's attempt this problem. In this problem, we have a configuration of bracket BC and link ABC. We do have an upper portion of link ABC and lower portion of the upper portion of link ABC is 3/8 inches thickness. So the thickness of this part is 3/8, and the thickness of each of these parts is provided to be 1/4 inches. That's the thickness of upper portion, and the lower portion, each of them has a 1/4 inch in thickness. There is a connection joint part from which connects the upper part to lower part with the length of 1.75 inches, and that's attached to each other by a resin, proxy resin. So that's applied in length of 1.75 and thickness of each of those cross section, which is a 1/4 inches. That's the area of the epoxy resin which applies it. And at the pin at A has a diameter of 3/8 and that's in a single shear condition. And pin at C is in double shear, as you can see in the figure. That's a two-part double shear condition and has a diameter DC is 1/4. That's 1/4. We want to determine first part. We want to know what is A, shearing stress in pin A, B, shearing stress in pin C, part C, largest normal stress maximum sigma in link ABC, D, average shearing stress on the bounded surface which we applied it, have a proxy resin, and at the very end, the bearing stress in link at C. The bearing stress not in pin but in link at C. Let's see how that works. So the very first step is drawing a free body diagram. Draw the free body diagram of this configuration. Have FAC apply at the top of the link ABC. This is A, and at the dx and dy. By making a moment about this point, we can cancel out these two forces. So summation of moment about point D goes zeros just gives us a 500 pounds times distance, which is 15 inches from D, minus FAC here, times 10 times distance from D, vertical distance from D, just gives us FAC is a positive 750 pounds. That's a tensile force. And if we want to know what is the shearing stress in pin A, let's go for pin A. That's again in single shear. Area DA is a 3/8 inches. And if that's a single shear with a diameter of 3/8, it just gives us shear at A is force of AC. If this is a tensile force, so tensile force pulls the link and at the same time pulls the pin as well. So there is a shear on pin that's due to the same force of AC. That's again 750 pounds over pi/4 times a 3/8 inches squared. And if you do the math, it just gives you almost 7,000 pound square inches, or 6790 pound square inches. And if you want to know what happens in terms of shear in PNC down below, that's a double shear, and diameter is a quarter of inches, that's 0.25 inches. So tau or shear at C is half of the force due to double shear condition. You can easily see from the part that's a double shear over the area of the pin itself. So that gives us 640 psi or almost 7.6 ksi. You want to know what is the largest normal stress? I need to provide you the distance of bits of this part. This is bits is 1.25. Should have provided problem statement data, but that's the same bits of 1.25 inches. So the largest normal stress is sigma F over area. And if we want to maximize C, we need to minimize C. So we need to go for happens at the minimum cross section. So sigma A is FACO over area net at the top. And if you look at the configuration, there is a condition that it just applies at the portion of this part, which is the thickness is like the top part, which is 3/8 inches. So the thickness is 3/8 inches times the 1.5, which is the length, minus area net. A net is just a subtraction of the pin itself. So we have a pin at the top by the diameter of 3/8 inches. So that's 1.5 minus 3/8, which is 0.375 times the thickness, which is 3/8, which is 3/8 inches. If you do the mass at denominator, the force of AC, which is 750 over net cross-sectional area, which is here, it just gives us a sigma A is equal to 750 over net cross-sectional area. It just gives us 222.19 psi or 0.2 ksi for the maximum normal stress, which happen at the minimum cross-sectional area, which occurs at top part of the link, because the diameter of the pin is higher at the top. If we want to know what is the average shear stress, so remember we are talking about there is a proxy resin applied at the connection of these two parts. So one at there, one at here. So that's a thickness of width of 1.5 times 1.75. That's the net cross-sectional area for each of the sides, either left or right. That gives us tau b is a half, just goes one of the area, half of the force applied at there, the half of FAC over 1.75 length over the bits which that shear applies on in terms of this the glue proxy resin which you use. It just gives us a bonding stress, or tau b is equal to 171.4 psi. And you can easily compare that with the shearing strength of the something like 2200, something like higher than that, and that's only less than 200. So proxy resin can handle far smaller amount of shear in comparison to other parts. And if you want to know what is the biggest stress in link at C, so link at C is a shearing area where you can apply a half of force, because that's again a part of that. Half of FAC is 275 over the area, which is thickness times the diameter. So that's the greenish area over here. That's the projection of this area This gives us a rectangle of 0.25 times 0.20 square inches. And if you apply that, it just gives us a stress of 6,000 pound square inches. And thank you. This example and previous video are a good sample of a application of different kind of shear, single in double scenario stress design. Thank you.